In the chapter of DC circuits, generally what you are asked to do is to use this formula, V equals to IR, and how are you going to apply it into these two arrangements, series and parallel? In each of these arrangements, you're going to have three rules each. And the three rules are going to be about what the current is like, how do you look at total resistance, and how do the potential difference add up or split up in that arrangement, right? So let's do a very quick 2-minute overview of the three rules concerning I, V, and R for both series and parallel, all right? So let's focus first on the series and parallel, but the series first, okay? In series, how does the current look like? We remember that the charges are going to flow from positive to negative. That's conventional current flow. So let's look at the current over here. The current here, if this is I1, will be the same as over here, I2, is the same over here, I3. The current is the same throughout the main path. There is no slowing down, speeding up of current, no such thing. There's no using up of current either. Current simply flows. If it's in the main path, the current in all the main paths will always be the same. So we have this. Now, why is this important? What you're going to do later is that you're going to ask yourself, this part over here, the current here I'm looking at, is it in the main path or is it in the split path? This is important because later on, right, as you go on to other things like this, you're going to have two different paths. This is the main path, and these two over here, these are the split paths. When we look back over here, all I'm saying is that as long as you're in the main path, the currents will always be the same. All good? Second up, what about potential difference? So let's look at the EMF over here. So let's first draw VE. All right, so this is the total. This is the total potential difference or the EMF of the power source, right? Which means across the entire thing, right? Across this entire circuit arrangement, right? This is how much I'm going to have. Now, it will split up this way. Some needs to be given over here, some needs to be given over here. Now, I would like you to take note that the length of this arrow does not denote how much it gives, okay? So don't take the length of the arrow as my magnitude. I'm just saying that it splits up between this and that, right? So if you were to look at the potential difference across this resistor, across the resistor, right? Because you're going to put your voltmeter across, remember? The potential difference across this resistor and the potential difference across the second resistor, these two will be equal to the potential difference across the entire thing, right? Or the EMF. So what you are trying to say is that the total potential difference or the EMF will be equal to V1 plus V2. Finally, what about the resistance? So let's use this color. R1 and R2. How do I find the total resistance? As long as it's in parallel, as long as it's in series, the resistance will add up. So RT for R total is equals to R1 plus R2. So these are the rules in a series arrangement, right? Where in the main path, current will always be the same, right? It will always be equal. Whatever current I have here will be the current here and the current here in the main path. When I see things in series, right, from point to point B, so to speak, I would know that the potential difference, if across the entire thing, is, let's say, 6 volts, okay? This plus this will be equal to 6 volts. It adds up when I go across in series. And how do I find total resistance? This plus that. Easy. What about for my parallel arrangement? Parallel arrangement is going to be a bit different. Let's look at the current over here, I. Now, the current over here in the main path is going to split into two. 1, 2. I1 and I2. Once it goes into the split paths, they split up. But once the split paths come back together again, they will combine back to its original amount, right? So I is equals to I1 plus I2. So this is the rule in parallel arrangement. Split paths over here, well, everything in the split path must come from the main path, right? So they split up. We must add up to get this one over here. What about potential difference? Okay, so I'd like you to see it this way. I don't think I drew this in class. I'd like you to see that everything here, okay, and since my points, my 2 points, sorry, here and here, these are only 2 points where there are actually components, right? So let's put it this way, okay? My VE. Okay, I could have stretched it all the way to the end, but it doesn't really matter because I'd like you to think of it in this way. I'm looking at that column. So I'm going to use my highlighter and I'm going to do this. See this? This is my total potential difference, so to speak, or my EMF. This is what I'm going to give for the entire circuit. And in this column, right, everything I have over here will be equal to everything within this column too. You see that? It'll all be the same. It'll all be the same. So what I do know, like we went through in class, is that the potential difference across this one over here, let's label it so that we can say it more carefully. This is R1, this is R2. The potential difference across R1, which is V1, because it's in that same block, correct? This block. Keep pressing the wrong thing. This block, right? Everything within this column, so to speak, will be the same. Which means, oh, let's not do that. Let's put it at the bottom here. Which means over here, V2, V1 will be the same as V2. The potential difference across these 2 points is the same as these 2 points, right? How is that the case? We said in class that if we looked at, let's say we put in numbers, right? And then we use the idea that we have in JC. Let's say this is 6 volts, right? Which means the potential here is 6, the potential here is 0, correct? As we move along here, nothing's being used yet, correct? Which means over here, the potential is still 6. And now if you trace backwards over here, if this is 0, over here is also going to be 0. Now, between these 2 points, the potential difference would be 6. So everything along here and everything along here, the potential difference is 6. Therefore, what we see over here is the rule when it comes to my potential difference will be my EMF in that column. If this is the only column we have, right, the potential difference there will be equals to V1, and that's also equals to V2. This is very important to remember the idea of the column, especially once we go to the complex designs, which looks something like this. Okay, and of course we get to that in a moment. All right, one last part. Let's talk about the resistance. What is the formula for resistance? In this case, we know that for let's put 1 over RT total. Okay, now just in case I'm not writing it well enough, I actually deem 1 over R and small t. Okay, so 1 over RT, the formula that we've done in class is that it's actually going to be NHCC in the SMS 1 over R1 plus 1 over R2, right? That's how you find the total resistance, correct? No, that's how you find 1 over total resistance. Later on, what you will have to do is you need to do the reciprocal. You need to flip the whole thing over, which is RT is 1 over the whole thing. You need to flip everything over. Because, hey, once you do this, right, that's not total resistance. It's 1 over total resistance. So you still need to flip everything over, which looks something like this, right? Which means the more resistors you have in parallel, the effective resistance will drop. Okay, that's 10 minutes. Now let's go on to try to solve and work out some of the questions which look very similar to this. Okay, now what is the method for solving these type of complex circuits or composite circuits? Well, here are the rules, or what are the methods? Number 1, you're going to try to simplify things as far as possible and make everything look like one big resistor, so to speak, right? So you see over here, there's so many things, right? There's this, there's that. So let's try to simplify as much as possible. Okay, what I mean by simplify, maybe let's do this. All right, let's try this over here, okay? So how do I simplify this one over here? Instead of 3 resistors, I want to combine resistors into 1 resistor to make things easier for myself, correct? Now I would tell myself, hey, these are in series. I know I'm just going to add up these 3 resistors. And when I do add it up, right, it will become as good as just 1 resistor like that, correct? When they add up. I mean, that's the idea of simplifying it. What about this over here? I have this. Ooh, this one looks a bit complicated. Let's simplify this. I can recognize that these resistors are in parallel. And I'm going to try to find the effective or total resistance of this, such that once I have the total resistance, it becomes as good as this plus the effective resistance there, right? I don't need to care about this part over here. Then after that, hey, this is complicated. I want 2 resistors. I want to find the total resistance of these 2. These are in series, so I find the total resistance in series, such that it becomes as good as just 1 resistor. So it's like taking away all the resistors and putting its equivalent amount inside. Okay, one more. This one. Which one over here looks complicated to you that you want to simplify? Can I make this in just 1? Yeah, I can, right? I would say that these resistors are in series. I can add them up. And that becomes as good as just 1 resistor, right? I forgot about this, right? Oh, now this. This are 2 resistors in parallel. I know a formula. I remember a formula that can make it simple. They can total it up. Of course, when you flip it around after that, I can simplify this, and this will become 1 resistor, correct? When I find this and this, so 1 over R1 plus 1 over R2, I flip everything around, I get this. Wait, now I got this too. I want to simplify it. How do I simplify that? Well, let's combine them. These are 2 resistors in series. Is there a rule that I know how to add up my resistors in series? Yeah, there is. This one, right? And once that is done, it's as good as taking just 1 resistor. I don't need 2 resistors. I'll just find the total of that. And once I add it up, it's as good as, right? Don't have these 2. Right? That's the idea behind it. But of course, the questions are not so straightforward. They don't always just ask you for what is the total resistance, right? That's where you need to use the rules in new ways, right? So what I just said over here is the basic idea of how do you find total resistance. You simplify it. So now let's look at some questions and let's see how to solve them. All right.